So question 13 then, and this is looking at how to calculate the relative atomic mass of an element from the abundances of each isotope of that element. Now, just to remind you, isotopes are where you have atoms of elements that have the same number of protons, so their atomic symbol doesn't change, the identity of the element doesn't change, but they've got different numbers of neutrons, so their mass number is different, and we can denote that with the mass number sometimes given after the name. So for example, carbon 12, carbon 13, carbon 14. Now with this question, we are told about two naturally occurring isotopes of copper, and that is copper with a mass number of 63 and copper with a mass number of 65. And we're told the abundances, how much of each of these there are. We need to give our answer to 2 decimal places, and we need to show all of our working. That's a really important thing to do in this type of question. So first thing to be really key about how we do this is you want to imagine yourself basically, and you want to imagine you've got a bag and it's got 100 atoms of copper in it. Okay, so there's 100 atoms in there. That is essentially what percentage tells you, is how many, if you've got 100 of that thing, how many of them will be this and how many of them will be that. So if we've got 100 atoms in our bag of copper, what this is telling us, this abundance, is that 69.2 of the atoms in that bag will have a mass number of 63. So I'm going to do 69.2 multiplied by 63, because that's going to tell me the mass of all of them. Okay. Now the remaining atoms in my bag, there's 30.8 atoms remaining, and they are all going to have a mass of 65. So if I wanted to find out the total mass of all of those, I would do 30.8 multiplied by 65. And now I've added those numbers together. That's given me the total mass of those 100 atoms in the bag. But I don't want to know that. I want to know the relative atomic mass, and the relative atomic mass is essentially an average atomic mass based on all of the isotopes. So to find a mean average, if we've got 100 of these atoms, we just need to divide it by the number of atoms that there are, which is 100. So we divide whatever we get here by 100. And if you do this calculation, you get an answer of 63.616. Now, we must recall that the question has asked us to give our answer to 2 decimal places. So I need to round either up or down. Well, it's 0.616, so 6 is bigger than 5, so I need to round up. So my final answer is going to be 63.62, and that is your final answer. Now, this question was worth a total of 3 marks. So if you did this bit, this equation, so you substituted the numbers in, you got a mark. If you got this value here, you got your second mark, and the third mark was making sure your rounding was correct, as was given in the question. Now, we've got a similar question here in part B, where essentially we're doing exactly the same thing, but rather than just 2 isotopes, we've got 4 instead for chromium. So again, you just want to imagine you've got a bag of chromium atoms, and you're going to pull them all out, and you're going to figure out the total mass and then divide it by however many you've got. So in our bag, we've got 4.3 atoms that have a mass number of 50. We've got 83.8 that have a mass number of 52. We've got 9.5 that have a mass number of 53. And we've got 2.4 that have a mass number of 54. Add all of those values together, you get the total mass of the 100 atoms that are in your bag, but we want to know the average mass, the mean, that's the relative atomic mass, so we divide this by 100, and if you divide this by 100, you get an answer of 52.057. That's no good because we want to give our answer to 2 decimal places, so we need to look at the second decimal place, it's 0.05. This number here, the 7, is above 5, so we need to round up. So therefore, our final answer is 52.06. The 3 marks for this question are available for, once again, doing this calculation here, subbing the numbers in, getting this answer out, and then rounding to 2 decimal places. And that's all there is to it for calculating relative atomic mass. It's just a mean average.